In this particular question, we've been given the rational function g of x, which is equal to 3x divided by x squared minus 4. And we've been asked to identify points of inflection as well as determine the intervals in which the function is concave upwards and the intervals in which the function is concave downwards. What I'm going to start by doing just off to the side is I'm going to rewrite that function in a manner such that I have factored the denominator. So g of x is going to equal 3x divided by x plus 2 times x minus 2. In this factored form in the denominator, what we can quickly recognize is that this function has two vertical asymptotes. The vertical asymptotes being at x equals negative 2 and x equals positive 2. It's important to identify vertical asymptotes because concavity can change on either side of those vertical asymptotes. The same is true as if the question had asked you to determine increasing and decreasing intervals. You would also have to consider vertical asymptotes and see if the function is changing from increasing to decreasing or the other way around. I know that wasn't asked in this question, but it's something that should be mentioned because you will encounter it in some of the questions you will obtain from the textbook. So we now know we have two vertical asymptotes. Well, the next thing we're going to do is find g prime of x. To do so, we're going to have to use the quotient rule. So in the numerator, we're going to have x squared minus 4. That's all being multiplied by 3. Subtract from that 3x times 2x. And then that's all divided by g of x squared, which in this case is x squared minus 4, all squared. In the next step, all I've done is expanded the terms in the numerator using my distributive property in the first case where I had the binomial multiplied by the monomial. So I find that g prime of x is equal to, in the numerator, 3x squared minus 12 minus 6x squared, and that's all being divided by x squared minus 4, where that x squared minus 4 is all squared. Combine my like terms in my next line, and so now I have my first derivative in the most simplified form. What I'm now going to do is take the second derivative, because I know that points of inflection occur when our second derivative is equal to 0 or when our second derivative does not exist. So again, we're going to have to use the quotient rule, and what makes this a little more challenging is embedded within that there is a chain rule question. So g double prime of x is going to equal, in the numerator we're going to have x squared minus 4 all squared times negative 6x. We subtract from that negative 3x squared minus 12, which is all multiplied by 2, which is in turn multiplied by x squared minus 4, which is in turn multiplied by 2x. And then all of that is divided by x squared minus 4, which is squared, which is in turn squared again. So in the next step, what I've done is I've looked at my terms in the numerator and I said, can I common factor anything out? Well, I can. I can common factor out a 2x and an x squared minus 4. And that leaves me within the squared brackets with an x squared minus 4 times a negative 3. Subtract from that negative 3x squared minus 12, which is multiplied by 2. And then all of that will be divided by x squared minus 4 to the 4. So now I take that second derivative and I set it equal to 0, and I continue to simplify that expression. I noticed from the previous step that there was an x squared minus 4 in the numerator, and there was an x squared minus 4 to the 4 in the denominator, so some division can occur. I've also done a little bit of expanding, and now I end up with 0 is equal to 2x times negative 3x squared plus 12 plus 6x squared plus 24, it's all in brackets, and then that whole thing is divided by x squared minus 4, which is all cubed. Combine my like terms in the next step, and I end up with 0 is equal to 2x times 3x squared plus 36, and that's all being divided by x squared minus 4, which is all cubed. And then I notice that I can common factor a 3 from the binomial in the numerator, and I'm left with 0 equals 6x times x squared plus 12, and then that's all divided by x squared minus 4, which is all cubed. So remember that points of inflection occur when g double prime does not exist, or when g double prime is equal to 0. So in the first case, I'm going to look at g double prime x where it does not exist. Well, it will not exist when x squared minus 4 equals 0. When I solve that, I get that x is equal to 2, or x is equal to negative 2. It's important to note that these were our vertical asymptotes that we identified at the beginning of the question. These values of x are not in the domain of our function, and therefore they will not be considered when we're trying to determine points of inflection. In the next case, we've got to consider where g double prime of x equals 0. So we want to set the numerator equal to 0. 0 is equal to 6x times x squared plus 12. And therefore, in that factored form, we know that either 6x equals 0, which gives me x equals 0, or x squared plus 12 is equal to 0. When I try to solve that resulting quadratic using my quadratic formula, you'd find that there's no real solutions. You didn't have to use the quadratic formula. You could have also just said x squared equals negative 12, x equals plus or minus the square root of negative 12. So there are no real solutions. So after I've got that x is equal to 0, I find the corresponding y coordinate by substituting back into my original rational function, and I find that y is equal to 0. So we've got the point 0, 0. Is it a point of inflection? Well, we're not sure at this point in time. So what we do is we put down our number line, and in this case, we now have to not only include the x value of 0, our potential point of inflection, but if you remember, we identified our vertical asymptotes at the first part of the question. So we must also consider those values and place them on the number line, because as we previously mentioned, concavity can change across those vertical asymptotes. So now we're going to test g double prime x at x equals negative 3, x equals negative 1, x equals 1, and x equals 3. These are x values found in my 4 different intervals found on that number line that I just drew on the left-hand side. So when x is equal to negative 3, I find that g double prime of x is equal to negative 378 divided by 125. So I place a negative there in that region of my number line. When x is equal to negative 1, my corresponding value for g double prime of x is 26 divided by 9. So I place a positive in that interval. When x is equal to 1, my corresponding value for g double prime x is negative 26 divided by 9. I place a negative on that region of the number line. And when x is equal to 3, my corresponding value of g double prime x is 378 divided by 125. So I place a positive on that portion of the number line. Now we've done all the work, we just merely have to make our conclusions. We know that a function is concave upwards when its second derivative is positive. Therefore, it is concave upwards when my x values go from negative 2 to 0 in union with values between 2 and infinity. It is concave downwards when my second derivative is negative. Therefore, it's concave downwards when my x values go from negative infinity to negative 2 in union with values between 0 and 2. And we now know that the point 0, 0 is indeed a point of inflection because concavity changed across that particular point.